Hello and welcome to the wolfSSL live webinar, Securing Medical and Industrial Connected Product using wolfTPM and ST33KTPM, presented by wolfSSL Senior Software Engineer David Gursky and ST Microelectronics Technical Marketing Manager Joe Pelosi. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from both SSL and ST Microelectronics, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at fact@wolfSSL if you have any additional questions. And now I'd like to turn it over to David and Joe to talk about securing medical and industrial connected product using wolfTPM and ST33KTPM.
Thank you, Shizuka. My name is David Garsky, and I'm a senior software engineer at wolfSSL. My co-presenter is Joe Pelosi from ST Microelectronics. And today we're going to talk about securing medical and industrial connected products using wolfTPM and the ST33KTPM module. I'll first give an introduction of our wolfSSL products, then Joe will talk about the TPM module. Then I will talk about wolfTPM and its features and capabilities and provide a live demonstration on an STM32H7. wolfSSL is found in almost every industry vertical. I think this is due to the fact that we're very modular and configurable and designed to work on embedded and high-end systems. Our company started in 2004 when MySQL needed a cleanroom implementation of the SSL library that matched their GPL licensing. And in 2006, we wrote the C version, which is the foundation of our library today. In 2014, we ramped up our company and the name to wolfSSL. Today we have over 2,500 OEM customers, 17 resale partners, and we secure over 2.5 billion connections all the time because we know of the products that we're in, which is pretty exciting. So these are our products. They're built around our cryptography engine wolfCrypt, which has been FIPS 140-2 and 140-3 certified. It's also been through safety critical certification at the DO 178 DAL A level. And then we have our TLS library that supports the latest TLS 1.3, DTLS 1.3, and the older versions as well. And we have a sniffer that's capable of decrypting TLS traffic if you know one of the keys being used. And we also have an MQTT client, an SSH client server that supports SCP and SFTP, our TPM library, which I'll talk about more in detail later. We have a secure bootloader, which actually supports pretty much all the STM32 parts out of the box, including the H7. We have an embedded firewall called Wolf Sentry, and it's an intrusion detection prevention system that can be used on embedded devices. We have a software-based true random number generator that is FIPS certifiable. We have a PKCS11 provider that uses wolfCrypt and can optionally use wolfTPM underneath. wolfHSM is a software-based HSM which can take advantage of any platforms that have a configurable secure core. Wolf Engine, Wolf Provider basically allows our cryptography engine to be plugged into OpenSSL. If someone wanted to leverage our FIPS module with OpenSSL, they can do that. We also have JNI, Java, C#, Python, JavaScript wrappers, including some other ones like Rust. We have all sorts of examples, command line utility, and then curl is part of our product portfolio, including TinyCurl, which is a smaller version. So ST is an important partner of ours. They've been very good at providing us new hardware for new platforms and making sure that we add support for those when we can. We also support a few of our libraries inside the STM32Cube MX tool, which allows for generation of code that can be used as a foundation for your projects. So we support TLS, MQTT, SSH, and TPM in these cube packs, which I will demonstrate later. So now I'm going to hand it off to Joe to talk about the ST33KTPM module.
Thank you, David. My name is Joe Pelosi, and I will be providing information about securing connected medical and industrial products using the first FIPS 140-3 certified TPM, the ST33KTPM2X. Visible attacks on connected products have driven government reaction, which makes securing the basis of a connected device's identity more critical than ever. The FDA requires connected products submitted for approval to have cybersecurity included in their submission for it to be considered. Using ST's FIPS 140-3 certified TPM to ensure a product is authorized to connect provides the strongest foundation to base security to meet those requirements. Other products need to meet FIPS 140-3 because our customers are serving government enterprises and they need to meet those requirements, which is another good reason to use our FIPS 140-3 certified solution. And here you see some other news items for governments that are also highlighting the need to be very secure, and that security will become a priority and good reason to be using TPMs in your application. FIPS 140 certified trusted platform modules are most used in enterprise PCs and servers, but are being integrated into many more applications as protecting product users and the visible OEM brands serving them against security threats has become very important. The next sector of products and OEMs using TPMs are infrastructure ones, and these also have been in process for a couple of years already, and they include gateway, base station, networking, access points, edge devices, and even car chargers. And then industrial and medical customers have begun using them, and this includes environmental sensors, actuators, HVAC, meters, factory automation, circuit breakers, IP cameras, copy machines, IP phones, and drones. And wolfSSL, ST's partner, has their wolfTPM, which enables TPMs to be used in many products having MPUs, MCUs, system on chip with cores running code. They can connect the capability of the TPM to provide FIPS 140-3 capability and other crypto services very easy and very fast. It provides the main specifications for our latest 40 nanometer ST33KTPM. There are two columns here. I'm not going to spend time on every field in the interest of not making this presentation too long. The industrial version has a 10 to 20 year life, whereas the commercial version only 10 years. Otherwise, they are the same in terms of the operational temperature range from -40 to 105 C. Very good standby power to support battery power applications, only 30 microamp standby, extensive crypto capability. You can't really find secure elements and secure micros with more extensive crypto capability than available in our TPMs, including even some support of Edwards curves and Schnorr for blockchain. And the product is upgradable to include post-quantum crypto as it is made available in the TCG spec and by firmware upgrade that we provide. We will be providing personalized versions of it, which in addition to the normal endorsement key, we will be initializing working identities according to the TCG specifications or recommendations for ID dev, and also an attestation key. These TPMs have a large amount of flash available for certificates or key objects or other secure needs to protect data for privacy. And the only other thing to remember is there's public data sheets available, but the full data sheet and some of the firmware upgrade materials and support require an NDA. It is useful to classify the strength of product security into 3 different types to understand why the ST33KTPM2X is so secure. Starting here on the left group, we have products that are based on microcontrollers and microprocessors offering mainly software-supported countermeasures against threats, and this achieves security. The most that can be achieved here is to minimize or remove errors that can lead to attacks on cryptography and keys. And these are non-invasive logical attacks. So you could say that the best that can be achieved is non-invasive logical attack resistance. In the center, you can have products that are based on the latest generation of microcontrollers and microprocessors with trust zones and other security features that protect keys. And these can be PSA or CSIP certified. And that shows that there's evidence that these security capabilities do work. They don't provide countermeasures against decapping the product or glitching I/O to a certain extent, or glitching the product with lasers or focused ion beam once they're decapped, or destructive analysis to read the flash. And so you can achieve here the same software resistance, product invasive resistance, and some level IC attack resistance to the extent that it can protect the keys from being retrieved from the outside. And then all the way to the right, you have secure micros like the ST33KTPM2X, which are certified and isolated from the code that's running in the main host. And these are fully tamper resistant and resistant against attacks that decap the package and try to retrieve the secrets by these other attacks that I mentioned here. So none of that is possible all the way to the right. So when the secure basis of the connected identity is based on an ST33KTPM2X and including personalization with a semi-custom root CA, it offers the greatest level of assurance that the product can meet security targets and even FIPS 140-3. I've mentioned the cryptographic basis of a device's connected identity several times, and this graphic shows how that works. On one side, you have the object that needs to authenticate, and on the other side, the authenticator. So this could be the system of which a surgical product is part, or a sensor connected to a patient is part, and here you would have the actual device itself. Both sides have a secret key and a certificate, which is the public key that goes with the secret key, that has been signed by a CA. So you can see that on both the object to authenticate and the authenticator. And the first step of the process is the authenticator asks the device or the product to provide its certificate. The device extracts the public key and verifies the certificate is valid using the CA certificate. It then sends a random number to the device or object to authenticate, which is signed with its private key that must be in some kind of protected storage, and the signature is sent and verified by the authenticator. So when these keys in the device or product are kept protected, then this process can be assured. I mentioned we can ship the TPMs personalized with a working identity. And to quickly go through that, we have the initial attestation key and certificate that we personalize, and also the IDEV ID key and certificate. And these are signed by a CA private key. We'll have a version of this product that is available off the shelf that we can ship with data that uses an ST key, and we can create customer-specific keys to enable ST to offer semi-custom versions to customers. The ST33KTPM2X's price always includes some level of secure personalization at our facilities, either the endorsement key and its certificate, which comes in the base device, or a full personalized version, as I showed in a previous slide, All the personalization is done at secure processes and facilities, starting from diffusion and test and packaging, and this is certified to common criteria in EMVCO. And at or after our packaging facility in Marcinese, Italy, we can further personalize, including the working identity using hardware security modules. And we do that so that this doesn't need to be done in our customers' products. So we can ship them later to our customers, including with data files, and they can install the cryptographic basis of the device's identity and be assured that it hasn't been leaked from ST either in this process, and it isn't feasible to get the information out through attack thereafter. If you're not doing this, you have to figure out how to securely implement this process at your subcontractors' facilities, which is not so easy or straightforward to do at times. By using wolfTPM, you can make use of the TPM's capability to secure your design and your products in a very simple way. It supports all of the functionality we've discussed in terms of pairing with the host processor, which prevents the TPM from being removed and used by non-authorized sources. It supports elliptic curve Diffie-Hellman for TLS, or secure key generation, secure boot, secure storage in the 200K bytes that I mentioned earlier. wolfTPM supports using the TPM, initializing the TPM if you're not taking it personalized already from ST, and makes the time to market in the FIPS 140-3 certification capability of your completed design very simple. If you're interested in evaluating the ST33KTPM, we have an evaluation board that is made for the Raspberry Pi ecosystem. You can see here the part numbers, and there's a link for, you can find its data sheet. It's very easy to wire this board into other ecosystems. So if you're interested, please let us know, and we'll connect you through our salespeople to get some samples as soon as you need them.
Thank you, Joe. Now let's dive into wolfTPM. So first I wanted to give a little history of the TPM 2.0 conception specification. It's developed by the Trusted Computing Group, and it was announced in early 2014. It provides a standardized set of API interfaces and physical hardware that's footprint, pin compatible footprint, a minimum set of algorithms and base features. So each vendor has to comply to these things, and it's tested, and you can actually choose between different TPM vendors, which makes it pretty attractive. It provides secure key storage and cryptographic interfaces for offloading keys. And currently it's found in most PCs and servers. It's used for UEFI and BitLocker, for example. It supports algorithms like RSA 2048-bit and ECC 256. Many of the vendors are increasing their RSA and ECC strengths as well. Supports measured boot, which means you can use it as evidence for the boot process. It has secure non-volatile storage that can be used. It also supports encrypted sessions where if there's sensitive data being sent to the TPM, that can be encrypted. It supports SPI, I2C interfaces to the hardware. There are a few other ones, but those are the most common. And most vendors provide a mechanism for a customer to be able to update the firmware on these modules. There's also a standardized endorsement key and certificate, which is created by the manufacturer to provide evidence of an authentic TPM. And it has an advanced policy management where you can apply policies to just about every aspect of the TPM. So we started recognizing a demand for TPMs in embedded projects quite a while back, even in 2015, where customers were asking for the ability to use a TPM on an embedded target. So we developed it, and our initial release was in February of 2018. We wrote it 100% in C because it's a very portable language, designed for embedded use for compact code size and minimal memory use with no external dependencies. So no external libraries are required to build the library. However, for some features, you do want to use wolfCrypt. And no memory allocation is required. So you're not required to use heap allocation. It can all be on the stack. It's supported and maintained by the original developers like me. We offer free pre-sales support, and it's licensed such that you can evaluate it with UPL v2, or you can acquire a commercial license for projects that require that. So wolfTPM is the only stack that is currently supported in bare metal. You might be able to port some of the other ones, but out of the box, our stack is able to run in bare metal without an RTOS. And we support all the different TPM modules, regardless of transport or hardware vendor. And we provide a stable API interface for using a TPM module across different operating systems and platforms. So we implemented all of the TCG required TPM2 APIs, and then we created wrappers to simplify common use cases. It has a built-in transport interface, allowing direct access to the hardware over SPI or I2C. And it supports parameter encryption using AES CFB mode, that's cipher feedback mode, or XOR. Authenticated sessions using HMAC or policy. And obviously you can build without wolfCrypt, but it does reduce some of the functionality. It does reduce code size. For example, if you're not using wolfCrypt, you can't import external private keys. You can't do parameter encryption. We have an ST cube pack for wolfTPM. With that, I'll demonstrate that more later. We also have support for Visual Studio and C#. You can use configure to cross-compile or even CMake as well. So common use cases we see are protection of a private key used for TLS authentication. So that would be the private key associated with the certificate that's presented during a TLS handshake. Also storage of a password. So for example, sealing a secret like a password that's used to unlock a hard disk or an SSD drive. You can do that based on an externally signed policy, which resolves that PCR brittleness issue that comes up sometimes. You can use it for measured boot, where you're extending PCR registers to provide evidence of a secure boot and a chain of trust. And we mentioned endorsement keys and certificates for TPM authenticity. Provide attestation of TPM-based data, which is just a built-in TPM feature. Secure non-volatile storage like one-way counters, and then cryptographic offloading. So we provide wrappers for key creation, import, export, basic cryptography operations for RSA and ECC, accessing the non-volatile storage for certificates or one-way counters, generation of certificates based on a key on the TPM and storage of those, the ability to unseal and seal secrets based on policies, attestation examples, endorsement examples for how to verify that a TPM is authentic, PCR policy and authorization. We have full TLS client server examples, and the demo today is going to be a TLS server that uses a TPM-based pre-provisioned key and certificate. So we support all the different transports. I didn't even mention the memory mapped IO, but it's another one. So you can do SPI or I2C. If you have a system that already has the transport interface, so like Windows and Linux already have their own TIS layer. And so you can disable our internal one and go directly to it through like the dev TPM 0 interface or the Windows TPM based services. And then we also support using a TPM simulator, which uses a TCP socket. So we designed it with a single HAL IO callback. So basically you can register your own callback to intercept all communication to the TPM. And we have built-in support out of the box for all the STM32 targets and all the other operating systems. Specifically on the ST33KTPM, like Joe mentioned, they have a semi-custom pre-provisioned device identity and attestation key that is provisioned during manufacturing and has a certificate that can be used for TLS. They also have endorsement certificates for ECC 256 and 384 and RSA 2048. So those are ones that are Endorsement certificates are created during manufacturing and show evidence of an authentic TPM. There's also a feature where they have GPIO control. I don't see many people use it, but it is something that's supported. So there are pins that you can use as input-output. There's also physical presence. Some TPM commands can be limited to actually require physical presence at the TPM to do certain functions. That's a policy you can apply. Okay, let's dive into the demonstration. I'm using a Nucleo board with the STM32H753ZI. This is also compatible with the H743, the only difference being the onboard cryptographic hardware. This is a Cortex M7 that can run up to 480 megahertz. For this demo, we're running at 400 megahertz. It has 2 megabyte of flash and 1 megabyte of RAM. I have the TPM module attached to SPI2 via some jumper wires. And I chose this board because it has Ethernet connectivity. The demo I set up has a TLS server using the TPM-based certificate and key, and it has a console, a shell on UR3 over the ST-Link. So I have posted the example here on this GitHub repository called wolfSSL-examples-STM32. And I've got it enabled with FreeRTOS, LWIP, and the wolfSSL and wolfTPM cube packs. So the UART shell will print out a DHCP IP address. You can run the wolf crypt test and benchmark, and you can show the TPM capabilities. The TLS server is just based on the example that comes with the H7 that has a web page it shows and also lists the FreeRTOS tasks. And I'll show you the certificate that is presented by the server. By the way, this feature in wolfTPM is enabled with this wolfTPM MFG identity build option. All right, so let's break out of here. So this is the GitHub repository I was talking about. And this is the folder that contains the example for the H7. I've outlined in here where I got the original example that this is based on, how the hardware is configured, and an example output. So let me show you the demo, and then I'll talk a little bit more about how I got it to happen. So I'm going to hit the reset button. As you can see, it prints out, I'm starting the demo, it prints out the shell, and then it'll eventually get the IP address over DHCP. And the shell has the options for the test and the benchmark, so I'm going to go ahead and run those. Let's see if I can make this. Yeah, this is good. Yeah, so it'll run through all the known vector tests that we have set up in our wolf crypt test. So it just proves that all the algorithms are functioning correctly. And then if you hit B, it'll actually run benchmarks on all these algorithms. Yeah, as you can see, the performance is quite good. These are millions of bytes per second for AES, and we'll go through GCM and SHA. And then it'll also go through ECC, RSA, Diffie-Hellman, Curve and Ed 25519. The reason that performance is so good is that we have I've turned on all the assembly optimizations for both the symmetric and asymmetric math, and I'll show you how to do that. By default, our build basically uses the C implementation of everything, but we do have assembly speedups for both ARM and Intel that are pretty impressive. So these benchmarks can also be found on the wolfSSL repository underneath IDE, STM32Cube IDE. There's benchmarks in there. Okay, so in the background, there is an HTTPS server running, and I've already got it open here. And when I refresh it, you can see it loads up. What happens is it makes an HTTP GET request for a web page, and the page is presented. The actual TPM is used for signing evidence that it has the private key. So it's offloading the key, signing there. The other thing I forgot to mention is at startup, what happens is the key is loaded from the TPM and also the certificate. Now the key, it has password-based authentication, and it uses a combination of a serial number and a master password that get hashed together. The master password for the sample devices is a known and published device master password, and it is in wolfTPM by default. Your own provision TPM will have a different master password. Okay, so now let's go. And by the way, all of this is based on the TCG spec for the device identity and attestation keys. That's what ST based it on. And yeah, this is the development board and the TPM. Okay, so what I wanted to do was go over to the STM32Cube IDE. So underneath the main.c, it basically initializes the TPM with a default IO callback. That IO callback for ST is here. We are manually controlling the chip select line, and we're using the HAL SPI transmit receive function on SPI2. And then go back here. So it will also run the HTTPS server and then run the shell. So the HTTPS server code is here, and it basically sets up crypto callbacks, sets up wolfSSL context allowing TLS 1.3 or 1.2, sets up a verification callback if you're using mutual authentication, then the interesting stuff. And by the way, all this code was pulled from the wolfTPM TLS server example that's out there on GitHub. So first it reads in the public key information for that pre-provisioned identity key. This is where the custom master password would be supplied by default. A null will use the sample. And then we export as dir the public key, and then we set that. So the TLS server needs to have some awareness of the type of key. So we make an allowance to be able to provide the public key to let TLS know, or TLS engine know. And then we read in the certificate, and then we set that with the use certificate buffer. And then the shell is really simple. It's just a task looking for a character on the UART that runs either the test benchmark or this capabilities information. I did have to add a delay in here because this task had a higher priority than the Ethernet task, and which was causing the link task not to be updated. Okay, and these two files here contain all of the build options for wolfSSL and wolfTPM. I did make a few customizations to this. I did want to open the IOC file, which is the cube pack file. But until then, let me show you the customizations I had to make. So if I go to code and then I go to the commits. So this was the stock example. This is the changes I made, and this is the patches after the generated code, which is not too many. There's just a few things. And there is this one issue with the 8-bit SPI that seems to come up on the H7. But the main thing was a few of the configuration build options, like turning on the ST33 and the manufacturer identity, that it's SPI2. I also turned on a delay between the polling functions. And then I turned on crypto callbacks and AES CFB, and also this define that allows public math operations to be used. I did turn on a GCM speedup to use GCM table 4-bit, and I turned on ECC 384. I turned on SES resumptions. I turned on LWIP support. I had to add a macro here saying that it was an H7 for this board, which I did upstream. And it turned on SHA-234. Okay, so going back to the IDE, this is the CubeMX tool that generates HAL code. We've selected FreeRTOS, LWIP, and the wolfSSL cube pack. You can see the options here. So the two options I wanted to cover were the assembly speedup options. So this is the math that's used for asymmetric ECC RSA2 I turned on the Cortex-M Plus assembly speedups there, and then there's also a new ARM ASM option. So this turns on symmetric acceleration for all of the SHA and AES. It also turns on curve and add 25519, cha-cha poly, a bunch of stuff's in there now. Okay. Oh, the other thing I wanted to mention is that on this example, normally when you first connect, it'll actually give you a warning that the certificate root of trust is not known, right? And that's because this sample does not have it's signed by a CA that I don't have in my trust store. But I did want to show you the certificate, right? So the common name is actually the TPM plus the serial number. And you can see it's issued by an intermediate CA that I don't have in my trust store. Otherwise, it'd be fine. Also, it uses SHA-234 and ECC 384-bit for the signing algorithm. But this is, I just wanted to show you that it was actually using the TPM-based certificate. And yeah, no, that pretty much wraps up the demo. Let me open this back up here. And now we're going to do a live question answer and answer any questions you may have.
Thank you, David and Joe. There's a question. How is the SPI communication from the STM32H7 MCU to the TPM secured?
Yeah, that's part of the, thank you for the question. So that's part of the TCG specification, and it's called parameter encryption. So when I mention AES CFB or an XOR, they have an allowance where if there's sensitive data, and it's usually the first argument of a command, that it can encrypt it in either direction. And each command is indicated if it could have sensitive data or not, and it gives the option to do that encryption. And wolfTPM makes that really easy to turn on and enable all the time. You can set up an authenticated session with parameter encryption at the beginning, and you can use that for all of your commands, and it'll automatically leverage it for ones that support it. So.
Thank you. There's another question. How does this kind of solution compare with IAR embedded trust? My understanding is that ST has also partnered with IAR to provide a similar functionality as what is described here.
I guess I can take a stab at this one, David. IAR is a partner for compilers that works with Wolf solution as well. This capability, the embedded trust, as I understand it, and I'm not an expert in microcontroller firmware development at this point in time, but it looks to me that enables the implementation of, for example, connected identity, as I showed in my slides, or David did with TLS, using the security features that are available in a micro like the STM32. And the resulting implementation would have a similar level of security as what I showed on that slide, with the continuum of security that can be implemented with and without a TPM. As an alternative, when you do use a TPM that's FIPS 140-3 certified, like our ST33KTPM2X, that connected identity basis is FIPS 140-3 certified. Whereas if you did it using the microcontroller features with the support of the IAR embedded trust, the customer would need to go and get that evaluated to FIPS if they needed that. And also it wouldn't be resistant to tamper as the TPM would be.
Thank you. And there's another question. Provided that I have a question down the road in my consideration of wolfSSL products, what is the best way to ask questions? And thank you for your time.
Yeah, that would be to email the support at wolfSSL.com. It goes into a Zenda system that's managed by us engineers. So yeah, you could also email fax at either one. That's FACTS at wolfSSL.com.
Perfect. And there's another question. TPM next question mark in the context of a PQC?
Yeah, so the TCG group is working on introducing post-quantum into the standards. Those haven't been made public yet. If you're part of the TCG, group, you can get access to those. I don't know what the timeline for that looks like, but there definitely will be post-quantum, officially supported in TPMs for certain. Yeah. Now that NIST has actually introduced draft standards for a few of the algorithms, that really helps.
And adding to that a little bit, our TPM is fully firmware upgradable, and we have a roadmap to support post-quantum crypto in the product. And NIST just standardized the algorithms, and we will be adding the capability within the next year or two as that becomes stable. And if you start with the firmware revision of the TPM as it is now, you can integrate firmware upgrade into your product. You can get that capability as we introduce it, and it will be certified. So you won't have to worry about that. ST will take care of it.
And there's another question. Does the TPM offer ECC functions using keys on the K1 curve?
Yeah, so that's Koblitz curves. Some manufacturers may support that. It's not typically used. I think maybe one of the blockchains uses it or something. Joe, do you know if
I
there's any
haven't
intention to support the K1?
I haven't heard that one before.
Yeah, it's
Maybe we
we
can
have
move on to another one
the
and get an
the
answer
NIST
while.
prime, and we have Brainpool and Koblitz curves. So I mean, they exist. We support them in wolfCrypt via software. I don't know if the TCG has any plans to introduce those into the TPMs. I honestly don't know. I would be curious to know what your use case is that is using the Koblitz curve.
So a colleague just answered me, sorry, Dave, to interrupt, and said it's not supported now, but it could be in the future. It's a curve used for Bitcoin, I guess.
Yeah,
It's explained to me.
that's what I remembered too.
Okay. There's another question. Do STM or wolfSSL have any product that target a use case where the TPM firmware is not run on the discrete device, but rather a remote core on a multi-core SoC?
I'm not sure how to answer that. TPM firmware is not on a discrete device. Oh, where possibly it could be run on something else. Joe, do you know how to answer that?
Yes, there are certain microprocessors available now that have something called a firmware, excuse me, TPM available. I mean, there have been, issues with those in the past in terms of, maintaining their securedness and flexibility. They don't necessarily um, support being FIPS 140-3 certified. And for example, in other markets like enterprise PC markets, they use discrete TPMs instead of those firmware ones because of the higher level of security attainable and the lack of foreseen high level security support. So and I'm not the STM32 marketing person. I don't know what we will be providing down the line in terms of those kinds of features embedded in the MPUs. We can find
It's
out.
an it's an interesting use case. Yeah, so not having a discrete separate chip, but actually running the logic, like a firmware-based TPM, but running it on a dedicated core or something else. There's a few customers that have indicated, requests for stuff like that. So that's an interesting use case.
Okay, thank you so much. And there's another question. Can you highlight some of the features that would drive a project to use a TPM versus using security features available directly on an MCU?
Yeah, I'll start with
Yeah.
that. So I think that's a great question, by the way. There's a few differences, right? So one is the ability to upgrade it if issues are found. In the security crypto that's on boards, the microcontrollers, it can perform well, but if there are eventually issues that would be really difficult to solve, you might switch back to software. But the TPM provides standard between all the different vendors, right? So standard interfaces, and it does provide a path to upgrade and certifications, obviously. So I know there's a few other ones. Joe, you have some more comments?
Yes, for sure. The most important one that I think was stressed in my slide is that our device is FIPS 140-3 certified. So that capability, that functionality is already certified for customers that must provide certified cryptography and capability for government applications and government customers. So you don't have to worry about certifying that particular functionality again, as it is integrated in other parts of the crypto stack throughout. It makes it easier. It's a building block to support that if it's necessary, because wolfSSL offers the awesome advantage of having FIPS 140-3 certified support as well. And the other very important thing is that the level of security that you get by using the microcontroller implemented security countermeasures is limited. It will never be as good as a TPM. And initializing the basis of connected identity in the micro is more complex. You have to kind of plan it, integrate it with the flashing of the micro and potentially secure hardware on production lines or in some infrastructure an OEM has to put a device in service. Whereas if in the case of the personalized TPM that ST can provide with the STM33KTPM2X, we ship it with that basis of connected identity already personalized in a secure facility, and the customer doesn't have to take care of it at all.
Thank you. There's another question. Why use a personalized TPM versus a standard TPM only shipped with an EK endorsement key?
Joe, will you take that?
Yes. So with the personalized TPM, we actually initialize an IDEV ID private key and certificate and an initial attestation key certificate. So this is a set of credentials in addition to the endorsement key that is the kind of the root of trust of the platform. And those can be used for the purposes of authenticating the product that uses the hosted device and the TPM as part of a connected system. So a customer using the personalized TPM, and if it's customized for them with a root CA that's only they can purchase, and the TPMs that we make for them, their systems can be enabled in advance to use those credentials that are already secure. And when we ship the TPMs, it's a secure micro and it's hardened for transport. You don't have to worry about it being compromised when it's shipping. It's been personalized in a secure facility, so no possibility the credentials are compromised there. They don't have to worry about it. And on top of that, we can provide bundle files of certificates. So we ship those to customers or provide them to OEM end customers that they can load into their networks, essentially whitelisting any of their products that integrate the TPM for connected identity.
That's nice. Also, the endorsement key cannot be used for signing external data, like for TLS authentication. It needs to be something like the IDEV ID. So there's a good reason to do it.
Okay, thank you, David and Joe, for answering all the questions. And thank you for hosting the informative webinar, and everyone for joining the webinar today. And don't forget to follow us on X at wolfSSL and at SD_world, as well as a LinkedIn and YouTube channel. And if you have any further questions, please email us at facts@wolfSSL.com. And thank you again, and see you next week for everything you need to know about FIPS 1.3. Thank you.